Although we went into quite a bit of detail regarding the representation of both positive and negative integers, remember the 2's complement discussion we had, we will not go into similar detail as far as real number representation goes. We will only give a few basic characteristics so that you know what kind of surprises you might anticipate. The scientific notation with the decimal system writes a number as a significand or mantissa times 10 to the power of an exponent. In the same way also, we can use the scientific notation to represent a binary number, a real binary number, using, instead of base 10, base 2. So it will be the significand, or mantissa, times 2 to the power of an exponent. Based on this notion, if we have 32 bits, you see on your slide how we could represent a real number. We will use 1 bit for the sign, 8 bits for the exponent, and then 23 bits for the significand. If we have even more bits, 64 bits, and keep in mind that 32 and 64 are not arbitrary numbers. When we talk about the types float and double in Java, you will see the similarity. So if we had 64 bits, we will use 11 bits for the exponent and 52 bits for the mantissa. This is an example that comes from the Start Concurrent textbook by Whitman, Matur, and Korb on how we can represent the number 10.5 in the decimal system. If you are interested, you can take a look to the details in that textbook, and I am sure there are many other textbooks that will have similar examples. We don't really care to go in the details of how this representation appears, but we do want you to get the basic understanding of how reals are represented. Probably the most important thing to keep in mind about the representation of reals is that they are not precisely represented in the machine. It is an approximation of the number that we can represent in the computer, not the actual number. Let's take a look at an example to see what we mean. This is a very simple program where we just print two numbers on the screen. We print 0.3 and then we multiply this number by 3 and we print the result. So obviously we would expect to see 0.3 as the first line of the output, and then the next line we probably expect to see 0.9. Let's now go and let me just bring back the program here so that we have it in front of us. Let me compile the program. We shouldn't have any problem, and now let's run it. What are we going to see? We do see the first line of the output to be 0.3. However, the second line of the output is not 0.9. It is something very close to 0.9, but not exactly 0.9. Why is that the case? This is because the number 0.3 is not represented precisely in the machine. It is an approximation of 0.3 that can be represented. So this small difference, it actually accumulates when we multiply this imprecise approximation, this approximation, by a number, by a factor. So when we ask for 0.3, we will not really see the difference, the approximation, but when we multiply the number, the approximation will be magnified, and this is why we actually see the difference.